Okay, this is the first video for chapter 8.5 for probability distributions and expected value. So first terms we want to talk about is random variables. When researchers carry out an experiment, it is necessary to quantify the possible outcomes of the experiments. This process will enable the researcher to recognize individual outcomes and analyze the data. The most common way to keep track of the individual outcomes of the experiments is to assign a numeral values to each of the different possible outcome of the experiments. For example, if we toss a coin 2 times, the possible outcome would be head head, head tail, tail head, and tail tail. For each of these possible outcomes, we could record the numbers of the heads, then the outcome of the outcome which we will label X is one of the numbers 0, 1, and 2, providing an immediate description of the exact outcomes of the experiments. This is the use of random variable. It's basically a function that assigns a real number to each outcome of an experiment. So this is a summary of that. And the other thing you need to know is the probability distribution, and we can ask you to build one on the test. Basically, it's a table that lists the possible values of random variable together with the corresponding probabilities. So it has the number and the probability. This is called a probability distribution. So make sure your probability in the probability distribution will add up to 1, because remember, probability is always add up to 0 to 1, right? Or 0% to 100%. So let's do one together. So the first one say, give the probability distribution for the number of heads showing when 2 coins are tossed. So if we are tossing 2 coins, con 1, con 2, then we can have head or tail, and each one can go to head or tail, right? So basically, the outcome would be, the first one is head, and then head, tail, and then tail, head, and tail, tail, right? So that's how we get the outcome. So 4 possible outcomes. The probability distribution of head. So let's try that. Probability distribution for getting a head, for tossing 2 coins. So we can have X is how many heads, and then probability of getting a head. So it could be 0 head, it could be 1 head, it could be 2 heads. That's all the possible outcome, right? And then we have a total here. And as you can see, 4 possible outcomes, so this is out of 4, right? And no heads, we got 1 of those, and because it's tail and tail, right? And then 1 head would be this middle 2, right? So it's going to be 2 out of 4, which is 1/2, right? And then 2 heads would be 1 out of 4 outcome, right? So totally we add 1, 4, 2, 4, 1, 4, we got 4 out of 4, so the total equal to 1, so that work. So normally they just give this number, this number, this number, and 1, okay? So this is the probability distribution table for tossing 2 coins with 1 is a head. So the second part, they want you to draw a histogram for using this probability distribution. So we can have, it look kind of like a bar graph, but those bars would be like connected together. So we can have 0 heads, 1 head, 2 heads, and then over here start with 0. My fraction, we have 1/4, basically 2/4 or 1/2, and then 3, 4, right? So this is the probability. So the title will be result we've had when tossing 2 coins. Okay, so for 0 we got 1/4. For 1 we got 2/4 or 1/2, right? Try to make them about the same size, like that. And then for 2 we also have 1/4, correct? So I'm going to say 1/4, 1/2, 1/4. So that would be a histogram using the data from the probability distribution table. Alright, so that's the B part. So this is the A part, this is the B part. Alright, expected value. Basically, when you calculate expected value, what you do is you use E of the X to represent expected values, and then you are going to multiply the X, the number, with the corresponding probability and adding x2, probability of 2 plus the third number times probability of the third number, and add to the last item on the table, which I'm going to call it x to the n, p to the n. So that's the formula for expected values. So see the first one, let's say maybe this is a table. Let's say this is about home sales. Home sales between January to April. So I'm going to say this is January, February, March, April, and 40% I'm going to sell 4 houses, 40% I'm going to sell 6 houses on the February, 5% for 8 houses, 15% for 10 houses. So we wonder, this is January, February, March, April, what would be the expected sales number of house in May? So we can do expected value will equal to the first number times the first probability, and then adding the second number times the second probability, adding the third number times the third probability, and adding the last number times the last probability, right? Let's see. So 4 times 0.4 plus 6 times 0.4 plus 8 times 0.05 plus 10 times 0.15, right? So my answer is 5.9. So if this question is about selling houses, and the first 4 months I sold 5.9 houses, then in May I can expect to sell 5.9 or close to 6 houses. I'm going to say expected to sell 5.9, so about 6 houses in May next month. But this is basing on the past data, right? So like now, if everybody is quarantined, staying in the house and losing jobs and not buying anything, probably this number will change. But if nothing change, basing on the past data, we will expect the next month we will sell about 5.9 to 6 houses. Okay. Alright, so that's how expected value work. How about number 3? Alright, the next question, they give you a histogram. So let's see. Is that better with this light? No. Let's see. something wrong with my computer. Okay. Example 3, they give you a histogram, and then they want you to find the expected value. So again, expected value, we basically look at the number times the probability, right? So this part is the number x, this part is the p of x. So 2 times 0.2, okay, plus 4 times, look like 0.3, and I know it's kind of tiny for you. This is 0.1, 0.2, 0.3, and this is 2, 4, 6, 8, 10. Okay, no, did I make this better or not? Okay, and then adding 6 times 0.2, and then adding 8 times 0.1, and then adding 10 times 0.2. Alright, so we're going to use our calculator just to multiply and add them together. 2 times 0.2 plus 4 times 0.3 plus 6 times 0.2 plus 8 times 0.1 plus 10 times 0.2. Okay, so I got 5.6. So basing on the past data, we will expect on average it's going to be 5.6, okay? Alright, number 6 and number 4 and 5 are a little bit more complex. The next one, say symphony orchestra. So suppose a local symphony decided to waste money by offering a HD TV for $400. So TV $400, a dinner for 2, just one dinner for $80, 2 CD for $20 each. So there's 2 prices here. A total of 2,000 tickets are sold for $1 each. Found the expected payback for a person who buy 1 ticket in a raffle. Okay, so what you want to do is first you want to build a probability distribution table. For prize winning, and you have to be careful, okay? So really think about it before you put down the number, okay? So this is x and p of the x probability, right? So a lot of people will make this mistake, and I'm going to show you what's happening. So you can want a TV which is $400, right? You can want a dinner for 2 which is $80, and then you can have, there's 2 prices for 2 CDs, right? Each is $20, and then you could win nothing. If you lost, then you will lose $1, right? You pay $1 already. Okay, but you have to be careful. If you want a TV, you don't actually get 400 because you pay $1 to get the ticket, right? So it's going to be 400 subtracting $1. So actually you won $399 for the first one. Okay, so a lot of time they don't put the step there, but I like to do that. And then if you want a dinner, you still have to subtract your $1 investment, so you're actually getting $79. And the next one, if you get a CD, you still have to subtract that $1, so that would be $19. Or you can lose $1. Okay, then we need to find out the probability, right? So I have a total of 2,000 tickets, which means I have only 1 prize for TV, 1 out of 2,000 of a chance you can get that. 1 dinner, so 1 out of 2,000 chance you can get dinner. 2 CDs, so this time I have 2 out of 2,000. And then if you lose, mean the total of 2,000 tickets, subtracting 1 of the TV, 1 of the dinner, and 2 of the CD, out of 2,000, right? So this will give me 1,996 over 2,000. Okay, so let's make sure the total add up to 100, okay? So this is 1, 2, 4, plus that would be 2,000 out of 2,000 equal to 1, right? So I think that checked out. Okay, now I have my probability distributions. I'm ready to do my expected value, right? Expected payback. E of the x is my expected payback. So the number times the probability, right? And then second number times the second probability, and then the third number times the probability, and then lost $1 times the probability, right? Okay, so you can, do it like the normal way, but I think it's easier if you will factor out, because each of these terms have a 2,000 in the denominator, right? So the easiest way to do this is pull out the 1 out of 2,000 to the outside. Then you will have 399 basically times 1 plus 79 times 1 plus 19. Oh, sorry, this is 2 times 2, and then minus 1 times 1996, right? So hopefully that makes sense. You pull out the 1 out of 2,000 to the front. So that means I just multiply this, and it will end up with a negative number. So it's not easy to win, right? Negative 1483. So it's negative 1483 divided by 2,000. If you use your calculator, you will have a negative of 0.7415, or about negative 0.74, right? Which means if you buy one ticket, you can expect, if you buy one ticket, expect to lose 74 cents. But if you really think about it, I mean, this is the official answer, okay? You can expect to lose 74 cents. But in reality, it's not really like this, right? If you buy a ticket, you kind of lose $1, right? So this is like in general, if you go like, if you do this over and over again for a long time. But if do the same thing over and over again, over a long period of time, basically you buy one ticket, you can expect to lose 47 cents. I mean 74 cents, sorry. It's really late in the evening now. Okay, so hope that makes sense. So that's why if you buy lottery ticket, a lot of time you lose money. It's kind of calculate like that also. Okay, very last questions. So the last question say, an insurance company has written 100 policy for $150,000, 500 policy for $75,000, and 1,000 policy for $25,000 for people of age 20. So they didn't tell us like if they want to insure for 150,000 how much to pay in each year for the policy. So that's not what they are dealing with in this question. They say if experience show that the probability that a person will die at age 20 is really low, right? So how much can the company expect to pay out during the year the policy was written? So this is not saying how much this company is going to pay for one person, okay? It's saying if they sell like 100 of this policy, 500 of this policy, 1,000 of this policy, then totally in a year how much they're going to pay, okay? So they probably will make a lot more money because when they sell the policy, they charge people, okay? Just want to make that part clear. And actually, the #1 job in the US is actuary. Those are the people who will calculate your risk and how much the insurance company should charge you. Okay, so let's do this. So again, this is expected value. We probably need a distribution table. So just like to be sure you understand, to find expected value, you first view a probability distribution. Table. Okay, let's do that. So this one is like a little bit complex. We have X and P of X again. The first policy is 150,000 policy, and then we have $75,000 policy. And this is if you die, you get that much money. If you don't die, you don't get any money, okay? And then $25,000 for this. Okay, so how many policy did they sell? So total policy is 100 plus 500 plus 1,000, right? So those are the number 100, 500, 1,000. Okay, together we have 1,600 policy, right? Okay, all right. So how many of them here? So you got 100 over 1,600. If you simplify it, it's kind of like 1 out of 16. Okay, the second one is 500 out of 1,600. Like personally, I would prefer to leave them as the same denominator, so I would have 5 out of 16. I think that's all, sorry. And then the next one is 1,000 over 1,600. So again, we can cancel that part, right? And then we got 10 out of 16, or you can write this as 5 out of 8, right? But personally, I think if you keep them the same denominator, it's going to be more useful. But in reality, a lot of time they reduce it to the lowest term, so those number would be the correct number in the probability distributions. If I have that, I can go ahead and find my expected values, right? Expected value is just this number times the probability, right? 150,000 times 1 over 16 plus $75,000, 5 over 16 plus $25,000 times, I'm going to use 10 over 16 because I want to pull out the denominator, okay? Double check my zeros. Sometimes I miss the zeros or something. That would not be good. Okay, so everybody have a 16 in the denominator, so I can pull out 1 out of 16. So that will turn this into 150,000 times 1 plus $75,000 times 5 plus $25,000 times 10, right? Okay. If you use your calculator and multiply together, we got 775,000 out of 16. So this is going to be $48,437.50. So this is expected values for payout for one person. And then we have to factor into, like, how about if that person actually died? So, and then expected death of people age 20. So this time we have 1,600 policy. Need to multiply the probabilities was 0.0008, right? So very low. So this means 1.28. So we need to use that number to multiply the payout. So factor in that. So we only, like, out of 1,600, only about 1.28 policy need to pay, right? So this is expected number of death of policy holder. Okay, so now if we do the expected payout for the $8,437.50 times 1.28, then we will get $62,000. So that would be the expected payout of the year. So again, this is out of 1,600 policy. They charge them for that 1,600 policy, so it probably way over this amount of money, and so the insurance company can still make money. All right. So this is 8.5.